Hello everyone. Today is the 33rd day of Leetcode 75 challenge. Let's begin with the 33rd question. Question number 104. Maximum depth of a binary tree. The level of the problem is easy. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a root of a binary tree. The depth of a node is the number of edges from root to the particular node. So this is basically the explanation what is a depth. So if this is a binary tree, then this represents a depth, right? You are going this way to the towards the leaf node, right? The maximum depth of a binary tree is the length of the longest path from the root node to the farthest leaf node. So basically, what is the depth of a binary tree, right? And first of all, what is a leaf node? If people don't know what is a leaf node, so a leaf node is a node which is at the bottommost part of the given binary tree and does not have any children nodes to it, right? This is the leaf node. And the maximum depth counts out to be the number of nodes from the starting root node, the last leaf node, and which has a maximum number of nodes in it. Fine. We return the maximum depth as the result. So basically, if you go from root node and explore all the leaf nodes, and the leaf node which has and the root node to leaf node which has the maximum number of nodes between them is the depth. In this case, this is the depth. Let me show you. In this case, this is the depth. Fine. What are the constraint of the problem? The number of nodes in the tree is in the range of 0 to 10 to the power 4, and the node value could be minus 100 to positive 100. Fine. I hope you understood the explanation. The problem is pretty straightforward. We have to just find the depth of the binary given tree, or you could say height also. Both represent the same thing basically. But yeah, that's the thing. Now let's move to the next slide. Let's understand the input output of the problem. So if this is the given binary tree, 3, then 9, 20, 15, and 7. Fine. What will be the depth? D means depth. Depth will be 3. Why? We start from the root node. If you come here, the depth is 2. Fine. If we come from root node to till this node, depth is 2. From this node to this node, depth is 3. From second node to seventh value node, depth is 3. So therefore, the height becomes 3. So this is what is it. The answer is 3 here. So I hope you understood this explanation. So now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Fine. So let's start by understanding the goal. So before that, let me draw a simple binary tree just for of our understanding. Fine. Great. So we are given a root of a binary tree right in this question, and our goal is to find the maximum depth, but which is basically the number of nodes along the longest path from the root down to the farthest leaf node. So we know these are the leaf nodes, right? And they're saying from root node to the farthest one, right? Here, if you could see, this is the farthest one, right? Great. And the depth is then how much? 1, 2, 3, 4, right? 4 is the depth. Now, what could the brute force, can come to your mind that, okay, we will traverse the complete, from root to leaf and we will store it in a list. We'll store all the values from the list, like list 1 for this one, iteration 1, right? Then list 2, the iteration 2 from here to here, then list 3 from iteration root to this node, right? And from there, which is the longest one, we take the maximum size of it, right? We could do that. So yeah, this could be one of the brute force solution. If something comes to your mind, please implement that. That will be a great one. Now let's look for the more intuitive and more relevant one. So instead, we could aim for recursion solution that naturally traverse the tree while computing the maximum depth efficiency. Right? If you might have got confused in this case, uh, what I'm talking about here. This basically means we will use recursion, right? And we'll try to count or measure the depth while traversing the tree. Fine, fine. So now let's try to visualize this process. Suppose we have a binary tree given. So let's just be the tree, right? And root to leaf paths are, let me write it down. 1, 2, 3, 4, 5, 6, with 7, fine. The route to leaf path are here 1, 2, 3, fine. Then 1, 2, 4, 1, 5, 6, then 7, fine. Among these, the longest path is this one, right? We can compute this by checking the depth of our left and right subtrees for each node returning the greater one plus one for the current node. Now, this could sound a more kind of complex one. Like how we can know about this? We could check that, okay, this is the left subtree. If we know what is the maximum depth, okay, of the left subtree and maximum depth of the right subtree, right? If we know that, we could check the maximum from left and right. Suppose the left one comes out to be the with the more value, right? So we take that maximum of left, right, and we add one because we have to include this node with us, right? That is why we take the maximum of the left subtree and the right subtree and add one to it because of the particular node where we are standing and comparing left and right? And we get the depth for that particular node, right? From that particular node to the leaf node. Fine. Okay, we could do that. So, and this will naturally lead to a recursive strategy that explore both left and right children for every node. Okay, so this is the thing which we understood. We could just take the left maximum depth and the right maximum depth. We could figure out that how we will find that depth, and whatever the maximum is left or right, we just add one to it because of the node from which we are taking out the left and right and returning. Fine. Now, how we can simulate this? Now let me make a tree here. Suppose if you're standing in a leaf node here and there are no left and right nodes, right? So if you remember, first of all, the answer for this tree is 3. Why? Because you basically count the number of nodes, right? So if there is only a single node, the height would be, or the depth will be 1. Fine. Okay, so you're clear with this. If we have only one node, the depth will be 1. Fine. So if you're standing in the leaf node, what we could do, we could see if we have what is the maximum in the left sub tree and the right sub tree, right? So since left is also null in the leaf node as we know, right? And right is also null here. So that's done, right? And what after that, what I said, we will just add one to it. Why? Because you're standing here and you're checking that what is the maximum of left and right plus the current node, right? Because it will also be get included in it, right? So that's the thing. And when we get it, we return it. So here we got 0 plus 0 and we returned 1. So we have 1 here. Fine. Then you go back, you are standing here, right? Then according to the iteration or even recursive approach, you will come here then, right? You will check, okay, left there is null, right? There is none. So it will return 1 from here. Fine. Great. Now the left iteration is done, right iteration is done. Okay. Because please keep in mind when we do recursion, we mostly go for left first, left, and when there is no more in left, we try to go to right. If there is no right, we go back. And from here we try to go to right if there is right? So this is the way the recursion is done. So that's the thing. So here you went left, left, and you got 1 here because left and right there is nothing and the particular node here. Then you went back, then you came to this part of the node, you got 1, right? Now you're standing in this node currently. Fine. What you will do? You will ask what is the maximum of left? Maximum of left is left subtree is 1. Maximum of right subtree is 1, right? So 1 both are same, so it will be 1 plus 1. So this will have 2 with it. Okay. Now it will go back and it will come here. Again, left there is nothing, right there is nothing. So it will say, okay, left and right both are null, and I myself have to be counted. So it will return 1 from here. Fine. And when after doing this part, it will go back and we will be standing in this part, last node or the root node. Fine. We will check what is the maximum of left subtree. It is 2. We're returning 2 from here. And the maximum of right subtree is 1. We're returning 1 from here. Fine. So we will have 2 from here, then plus 1, and we will get 3. Right. So this node will return 3. So this is how we get the depth of the binary tree. Fine. Fine. I know this might be a bit confusing for few of the people to understand that how the recursion is working. For this, the knowledge of recursion is must. You should have cleared knowledge, and I will request you to clear your knowledge regarding the recursion, do the basic questions related to it, how the recursion works, and all that stuff. Then please come to the video again and look at a solution. I'm sure you will understood how it is done, right? So that's the thing. So this is what I have written here. We will create a helper function that computes the height or the depth of a subtree. Okay. And the current node is none. We return zero since there is no depth like in the leaf node basically. And recursively we will call the height functions again and again, having taking left and right children. For each node, we will take the maximum of the left and right subtree as I discussed here and add one for the current node. And finally, we will return the maximum depth, which is the given main function, and we will call height. That's the thing, right? So from here, what we figure out? We figure out that we applied a classic recursive strategy to traverse the tree in a depth first manner. Depth first manner, it is known as the DFS traversal. Okay. And at each node, we calculated the depth of its left and right subtree and used the greater one. Fine. So while going in the depth, we didn't do anything. As soon as we encountered a null value or the leaf node, we just returned one with it, or the maximum of left or right plus one. And we checked for the right subtree. Then we got a value, we returned it, and we checked which is the maximum from both, and added one to it for the current node and return it back. Right. This is the thing which we do. And for understanding this in much more clear how recursion work, I will urge you and I will request you to look at the recursive videos that will make it more clear for you. Fine. Now let's move to the next slide. I hope you understood the intuition. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. Fine. Okay. Let's start with the handling the base cases. For example, we we check for the root if it is none. Suppose we are not given a tree only, right? There is no depth then. Fine. So we'll return zero, of course. Fine. That's the thing. And after that, the act as our base case in the recursion to stop further calls because if trees does not exist itself, so it does not make any sense to go for further, search for it or further operations, right? Because trees with no nodes don't contribute in the depth. Fine. Now, second step will be define a helper function to compute the height. Fine. What we will do, we will try to write a helper function which will compute or calculate the height. Then how that helper function will work? We'll pass the root node to it to compute the depth of a given subtree. Fine. If the root is none, we return zero, of course. No depth was found. For example, if this is the tree, you're standing here, nothing is here, right? So we'll return zero, of course. Then if you go and check here, there is nothing, we'll return zero here, right? And that's the thing. So we recursively will call height of root left to get the depth of the left subtree. And this is what I explained to you earlier also. In recursion, until and unless the base case is triggered or plotting action, it will keep on going to the left. In our case, we are taking it to the left, so it will keep on going in the left. Okay, and soon as it encounters a base case, it will go back and look for the right one. Fine. Then we will recursively call the root right to get the depth of a subtree. We return 1 plus maximum of left and right to count the current node and the longer path. This is the thing which we discussed in our intuition approach also. This is the exact thing which I wrote here. Now, why this? Because this allows us to explore both subtrees and compute depth bottom up by combining recursive call. Fine. Where what we are doing here bottom up approach because first we are going to the bottom, we're finding a value, we're returning it to the topmost path. Fine. So that's the thing. Now in step 3, we call the helper function from next step. So this is the function which will calculate the height, and this function will be called in this particular given function in our problem. Fine. So that's nothing to worry about. Once the helper is defined, simply we return the root from the maximum depth function. So basically, max depth is a function given to us in the problem. Fine. We make a helper function within it, right? We code it out and we call it in within this function itself, right? This kicks off the recursive traversal starting from the root node. The final return value gives the maximum depth of our entire binary tree. Fine. This is done because delegating the logic to helper function keeps the main method clean and readable because max depth is a given function. Fine. So if we code it within it, it will be cluttered, right? So instead of that, what we tried, we created a helper function here and we code it out somewhere else. Fine. And when this particular helper function is resolved and run successfully, we will get the value in here and we will return it. Right? That's the thing. hope you understood the approach. And now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So this is the given function to us. Fine. If root is none, we return 0, of course, as we discussed. Then we created a height function where pass is the root node. Fine. So here we are calculating the height. If the root is none, we return 0, of course. Then we go to the left node until and unless we encounter left node to be a null. If it is a null, then we go to the right, come back and go to the right one. Fine. And when both is done, both iterations are done. For example, if you are here, left nothing, null, right nothing, null. Fine. So you're standing here, then you return this calculation. And when this complete thing is done, we return the height of the given root node. The time complexity comes out to be O of n because in the worst case, you might be traversing all the nodes. Fine. That is why the time complexity comes out to be O of n, and the space complexity O of 1 because we are not using any extra data structure to store the values. Fine. So I hope you understood this code. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at a dry run of the example. Fine. So this is a dry run. Let's do it. Fine. 3, 9, 6, then 8. Okay. Now let's do the dry run. Okay. We start with the root node left. We call height function recursively and we go to the left node, right? So we came here, we're standing here, then here. Okay. Then we check for the root left. It is null. Fine. Okay. So this iteration is done. Call is done. Then we come to the right call. From here, the right call, we get null. Both are null. Fine. So if both node are null, we return 0 from there. So from here we get 0. From here also we got 0. Fine. From maximum of both the zeros plus 1, this has one value now because 1 plus maximum of left subtree and the right subtree, which comes out to be 0. We have returned 0 successfully. This is done. So basically the height of the or the depth of this particular tree is 1. Fine. From now we go back. Now from here we come here. Okay, we check for the left subtree, it is null. And also from here the right node, it is also null. Fine. So this returns 0, of course. And 0 is the no right and left both are 0 and plus 1. So this tree returns 1. Fine. Let me clear it up. Okay, so this is done. Now we're standing here in this tree. The left subtree height is 1. Right subtree height is 1, right? So instead of 0, 0 here, we will have 1 and 1. A maximum of 1 and 1 is 1 itself, and plus 1 we get 2. Right? So height of this subtree is 2 at the end. Fine. So it will return 2 as the height of its tree. Fine. Now from here we come back, we go here, then we come to the left, then we try to come to the left, we see it is null. Fine. So we return 0 and we go here, and we can come back, then we come here, then we come here. Again we got null, so we return 0 from here. Then we come to this node, right node, we return 0 from here. So from 0 and 0 plus 1, it comes out to be 0 plus 1 gives me 1. Fine. So height of this subtree becomes 1 with the value 10. Clear this up. So height is 1. Fine. So now it returns back. And left subtree height is 1. Right subtree height is 0 for this node. So it comes out to be 2 now because maximum of 1 comma 0 is 1 plus 1 gives 2. Fine. Great. When it comes here, again the height of this tree comes out to be 1 and returns 1 from here. It returns 2 from here, and maximum of 2 comma 1 is 2 plus 1, it's 3. Fine. Great. Now this tree, the left has the 2 and it returns 3. So maximum of 2 and 3 is 3 plus the current node 1 gives me 4. Fine. So the height of the or the depth of the complete tree comes out to be 4, which is our output. Fine. I hope you understood the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition. And if you don't have the knowledge about how recursion works and how what is the tree structure works, please go and learn about them. then come back, then look at the approach and the code, and after that do a dry run by yourself on 2 3 examples, and I'm pretty sure you will understand the process behind it. Now let's move to the next slide. Now since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Our first condition was to check if root is none, return 0. Fine. Otherwise return self dot, we create a function height where we will send root to it. Then define height. Root is none. Here also we return 0. And we will go to the left. We will keep on going to the left until and unless we encounter the base case. Then if the base case for left is encountered, we go for the right. At the end, return 1 plus maximum of left comma right. Fine. So this is our solution. Now let's try submitting it for the basic test cases. So there's a spelling mistake here. Let's again. Okay, it got accepted. Now finally submit the solution. Okay, we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.